Welcome to this video guide on the particle model and internal energy. This is a core topic for your GCSE Physics exam, and we'll be covering everything from particle arrangements in solids, liquids, and gases, to how heating affects energy and state changes. In this video, we'll break down the particle model, explore how particles move, define internal energy, discuss changes of state, and provide essential exam tips to help you succeed. Let's begin with Chapter 1, the particle model. At its heart, this model teaches us that all matter is made of tiny particles, and the way these particles are arranged is what determines the properties of a substance. The fundamental idea is that every substance is made of particles too small to see, yet their behavior explains everything around us. This model is essential for predicting the behavior of matter, and is a recurring topic in GCSE exams. A key rule in physics: particles never stop moving. Even in a solid, particles are constantly vibrating. This motion is called kinetic energy, and it's directly linked to temperature. The hotter the substance, the more energetically the particles move. The particle model explains the three states of matter. Solids have particles tightly packed in a regular structure. Liquids have particles close together, but arranged randomly, allowing them to flow. Gases consist of particles that are far apart and move rapidly in all directions. In solids, particles are held in a regular, tightly packed structure by strong forces of attraction. They cannot move freely, but vibrate continuously around their fixed positions. As temperature rises, these vibrations increase. In liquids, particles are close together but aren't held in fixed positions, allowing them to slide past each other. This is why liquids can flow and take the shape of their container, while still maintaining a definite volume. Gas particles are far apart, with large amounts of empty space between them. They move randomly and rapidly, meaning they have no fixed shape or volume. Unlike solids or liquids, gases can be significantly compressed. This table summarizes the differences between the three states of matter regarding their arrangement, motion, shape, volume, and compressibility. It's a great reference for your revision. Moving on to Chapter 2, kinetic energy and temperature. Understanding how these concepts link together is central to your GCSE Physics studies and a very common topic in exam questions. When you heat a substance, you transfer energy to its particles, causing them to move faster and gain kinetic energy. In solids, this means more vigorous vibrations, while in liquids and gases, it means faster movement and more forceful collisions. Kinetic energy depends on both mass and speed. The equation for a single particle is shown here. It's important to remember that as speed doubles, the kinetic energy quadruples, a crucial definition for your exams. Temperature is a measure of the average kinetic energy of the particles in a substance. Always remember to include the word average. Missing it in an answer can cost you marks. Finally, cooling a substance transfers energy away, causing particles to slow down and lose kinetic energy. At absolute zero, which is negative 273 degrees Celsius, particles have the minimum possible energy, and all motion effectively ceases. This slide summarizes the relationship between temperature and kinetic energy. High temperatures correspond to fast-moving particles and higher kinetic energy, while low temperatures indicate slower movement and lower kinetic energy. Now let's look at Chapter 3, internal energy. It is important to realize that internal energy encompasses more than just the kinetic movement of particles. It is the total energy stored within a substance by all of its particles. Internal energy is the sum of kinetic and potential energy. Kinetic energy relates to particle motion and is linked to temperature. Potential energy is stored in the forces or bonds between particles and relates to their position and separation. This comparison highlights the difference between the two components: kinetic energy, which determines how fast particles move, and potential energy, which relates to the interparticle forces and changes during state transitions. Heating a substance increases its internal energy. While this often increases kinetic energy and temperature, during a change of state, energy is used to weaken interparticle forces, which increases potential energy instead, keeping the temperature constant. Cooling is the reverse process. As energy leaves the system, particles lose kinetic energy, move slower, and temperature drops. Forces between particles also become stronger, as the substance may transition between states. This formula relates energy transfer to mass, specific heat capacity, and temperature change. Remember for your exams that this formula is specifically used when there is a change in temperature without a change of state. Moving on to Chapter 4, changes of state. It is a critical concept to understand that heating does not always raise temperature. Sometimes, energy is diverted entirely into changing the state of the substance. Changes of state like melting or boiling occur because transferred energy helps particles overcome the attractive forces holding them together. This extra energy allows particles to move more freely, transitioning from one state to another. Particles naturally attract each other, To transition between states, particles must overcome these forces. The energy required to change state without increasing temperature is known as latent heat, which is stored as increased potential energy. A key takeaway for your exams: temperature remains constant during a change of state. Because the energy is increasing potential energy rather than kinetic energy, the temperature does not rise until the transition is complete. A heating curve illustrates this concept clearly. The rising sections show temperature increasing with kinetic energy, while the plateaus represent state changes where energy increases potential energy while temperature stays flat. This diagram provides a complete overview of all possible changes of state, showing the transitions between solids, liquids, and gases. In Chapter 5, we explore the particle model in action. Beyond internal energy, this model also perfectly explains everyday physical phenomena like diffusion and thermal expansion. Diffusion is the net movement of particles from areas of high concentration to low concentration. This occurs naturally due to the constant, random motion of particles in liquids and gases, requiring no external energy input. Diffusion rates depend on several factors. Higher temperatures provide more kinetic energy, speeding up particles. A steeper concentration gradient increases the rate of movement, and smaller, lighter particles diffuse faster than heavier ones because they travel at greater speeds. When substances are heated, their particles gain kinetic energy and move more vigorously. In solids, this increases vibrations. In liquids and gases, particles travel further apart. This causes materials to expand, a principle used in thermometers, bridges, and hot air balloons. Contraction is the reverse process. As particles cool, they lose kinetic energy and move less, taking up less space. This contraction is why structures like railway tracks and bridges include expansion gaps to accommodate seasonal temperature changes without structural damage. The particle model provides a consistent explanation. Heating adds energy, leading to more movement and expansion. Cooling removes energy, reducing movement and causing the substance to contract. It's all about how much space the particles require based on their energy. We are now moving to Chapter 6, Key Exam Tips. Avoiding common mistakes is the best way to secure those extra marks, so let's walk through some specific pointers for your upcoming assessments. Remember this top tip. Temperature is defined as the measure of the asterisk average times kinetic energy of particles. Always include the word average in your exam answers. Because particles move at different speeds, temperature represents the mean value across the entire substance. Avoid these common traps. Distinguish between temperature, which is average kinetic energy, and internal energy, which is the total kinetic plus potential energy. Also, remember that during state changes, energy affects potential energy, not kinetic, and that solid particles vibrate. They never truly stop. For state changes, remember three things. Temperature remains constant during melting and boiling. Latent heat is stored as potential energy to overcome interparticle forces. And state changes are reversible, with energy released during freezing equal to the energy absorbed during melting. This table provides a quick-fire reference for key terms. From the definition of the particle model to latent heat and thermal expansion, keep these concise definitions in mind for your revision. You've made it to the end. To summarize, all matter is made of moving particles. Temperature is the average kinetic energy. Internal energy includes both kinetic and potential energy, and state changes require latent heat. You're well prepared for your exam. Good luck!